All right, hello everyone. This is Ms. Piekarski again. I am just going over how to find the slant and behavior asymptotes. And this is a page that we saw from a previous video about your horizontal asymptotes and compare the degrees of the numerator and the denominator to see if you have a horizontal asymptote or a vertical or behavior asymptote. All right, so we're focusing on here. Anytime the numerator's degree is bigger or greater than the denominator's degree, then you're going to have either a slant, oblique, or diagonal asymptote or an behavior asymptote. And something that you'll figure out pretty soon is that if the numerator's degree is just one more than the denominator's degree, then you're going to have a diagonal asymptote. If it's more than one, so let's say you had x to the third power over x, okay, to the first power. So again, remember, if you don't have an exponent, then the exponent is 1. So in this case, your 3 is 2 greater than 1. So this graph would have a behavior asymptote. And then if you had, let's say we had x squared, or hey, let's say we had x to the 5th power, that's supposed to be a 5, over x to the 4th power, where the difference is only 1, then you would have a diagonal asymptote. Okay, so in this case, your numerator's degree has to be greater than the denominator's degree. So let's look at what we do in those situations. First of all, let me see, I think I had this in the previous video, right? So we're looking at, let's see, right here we have the numerator's degree is greater than the denominator, and right here. So this graph would end up having, because, nope, these are both going to have diagonal asymptotes because it's just one greater. All right, those are examples, and I think I just covered all this. Let me get rid of some of this stuff so you can write it down. So a slant, some places they call it slant, some diagonal, some oblique, all the same thing. It just depends on the terminology. Okay, so a slant asymptote is neither linear, a slant asymptote is a linear asymptote that is neither vertical nor horizontal, and instead it's going to be at a diagonal or slant. Okay, to find the equation for your slant asymptote, you're going to divide your numerator by your denominator, and then whatever your answer is, the quotient is your answer, and that's going to be where your where your diagonal asymptote is. Okay, so in this example, in the example in your notes, this part is where the slant asymptote is. And you just set that equal to 0 and you can graph it, and you'll see where it is. Okay, your notes do show you how to do long division. It's the same process that you learned in 5th grade a long time ago, except this time we have variables and numbers. And so let me go through the process with you. In this case, your equation's 2 times x squared minus 7x plus 7. And then in the denominator, or you're going to divide by x minus 2. And the trick is you want to ask yourself, what do I need to do to this value here to get 2 times x squared? Okay, and you want to match those up precisely. So to get 2x squared, you have to multiply this x by 2x. Okay, and so you would say 2x times x gives you 2x squared. But then you have to say, okay, well, there's this another term here, so you need to also multiply this term by 2x. So 2x times negative 2 is negative 4x. Okay, write it down like that. But then when you're doing long division, whatever you have here is going to be subtracted by whatever you have up here. So instead of having a positive 2x squared, you end up with a negative. And then instead of having a negative 4x, you would end up having a positive, because if you distribute this negative sign here, it would make the 4x become positive. So that's how this negative 7x plus 4x becomes negative 3x. Okay, and then you're just going to repeat the process. You also need to carry down the next term. So do you see how they carry down the 7? So now we want to know, what do I need to multiply this x by to get negative 3x? Well, x times negative 3 gives you negative 3x here. And then negative 3 times negative 2 gives you positive 6. And again, we're subtracting, so this negative 3x is going to become positive, and this positive 6 is going to become negative. So the remainder is just going to be 7 minus 6 gives you 1. Now, the interesting thing about the remainder is you're totally going to ignore it for the when you're looking for your slant asymptote. You totally ignore the remainder. Do not include it. Okay? So that's how they get your quotient. The 2x minus 3 is the location of your slant asymptote. Okay? And here's an example of the graph that they just did for you. Okay? Other parts of your notes, let's see. And behavior, same kind of thing. You're going to divide the numerator by the denominator. But in this case, because you have a degree of 3 here and a degree of 1 here, your quotient is going to be x squared. It's going to start off with x squared. So the whole thing in the notes that you need to write down, it's still the same thing that you had for the slant asymptote. The formula for the end behavior asymptote is going to be whatever your answer is when you divide your numerator by the denominator. Okay, the quotient just means whatever the answer is. Okay, go ahead and read over this. You might want to highlight this part. Whoops, forgot I changed it to selecting the 2 or more degrees greater than the denominator. That part you need to highlight. All right, so let's look at a couple more examples. This should also be in your notes. And you see how they took this equation, divided it by x plus 1. You can go through the whole process. Remember, you're always subtracting down here, so you're going to end up just changing your signs. You always drop these terms down. The remainder does not matter at all, so we can just, like, once you get down here, you don't need this. You can cross it off if you want to. I don't care what the remainder is. And then in this case, our answer is, instead of just a linear equation, it's a quadratic equation. Okay, and then you can graph it and find the answer. You can graph both this equation here and this equation, and you'll see that this is a rational function, and you'll see that this part, the quotient, actually is an asymptote that just kind of hugs part of the graph. So let me pull it back up here, and you can see what I mean. So this graph here is the quotient, or the answer, when you take the numerator divided by the denominator. Okay? And let's see. One thing that you should note, and I know lots of you would probably really prefer the synthetic division over long division, because it's just a little bit more complicated. There's more things you have to worry about. You can use synthetic division sometimes if your denominator just has a variable and then plus or minus some number. Okay, so that's the only time you can use synthetic division, if it's linear. Okay, and let's look at, I think I did one more example in the notes. Yeah. So right here, this is actually one of the problems that we're going to work on Friday in class. So those of you that come to class, you'll already have this answer. Go ahead and go through it. You can see how I added several zeros, because in my numerator I just had x to the third, so I was missing x squared, x, and my final 0. Okay, so I added all those terms so that I can get my quotient up here. And then you can go look through the process and study it. Notice I just changed the signs as I was writing them down. I didn't do both signs. Just gets a little bit complicated. I will go through this process with you in class Friday, and you can watch this video over the weekend if you're struggling. When I graph this equation up here and my quotient right here, this is the picture I get. So you get this part here and this part down here, and notice how the the asymptote here really gets close. In fact, it looks like it's right on top because it matches so well. Okay, and let's see. I think, oh, here's another one that I did. I did the same process here, but with synthetic division. One thing you should note is that, let me change it to pencil. My my factor is, or in my denominator, I have x plus 2, but in my synthetic division, I used a -2 here. The reason why is because the number you put here is whatever the solution is. So in order to find the solution, you have to set this factor equal to 0 and solve for x. So we have x plus 2 equals 0. When you solve for x, you get x equals -2. Okay, so that's why in my little corner box I have a -2 and not a +2. Okay, once you get this set up correctly, then the whole process that we used for synthetic division in our last unit, it's exactly the same process. Carry it down, multiply by whatever you have here, write the answer here, add, and so on. Okay, so in this case, I have, this is my quotient, and so my graph, when I graph it, looks like what I have here. And behavior asymptotes are really, really cool. It looks amazing how the graphs kind of just match so well. It's awesome. These are one of my favorite things to do with rational functions. So these are 3 of the problems we're doing in class on Friday. You might want to write, if you missed class on Friday and you're watching this over the weekend, you might want to write these down and work on them on your own. You will need to find your horizontal asymptote, sorry, not horizontal. You need to find your x-intercepts, y-intercepts, your vertical asymptotes, removable discontinuity if you have it, and then what the equation is for the slant or end behavior asymptote. Here's 3 more of the equations that we're doing on Friday. We will go through some of these in class. I'll probably have the students like pick one from each page and then they get to do the rest on their own. Okay, so work on these. I will probably not get through all 6 of these problems in the textbook, or excuse me, in class. And then the rest will just be homework. So these are going to be due on Monday. All right, I hope this video was helpful. If you have more questions about slant or end behavior asymptotes, you can look in your notes. Also, I'm sure there's more YouTube videos on slant and end behavior asymptotes. Okay, see you guys in class on Monday.